Okay, so let's start. So first of all, I'd like to thank the organizers for providing me this nice chance. I'm Shinichiro Akiyama from the University of Tokyo. And today I'm going to talk about the so-called tensor renormalization group approach, particularly to the higher dimensional lattice field theories. And here is my plan of today's talk. Well, first of all, I'd like to briefly explain what is the TRG approach. And after that, I'd like to explain how to extend the algorithm to investigate the lattice fermions. And thirdly, I'd like to report our first application of the TRG approach to the four-dimensional lattice gauge theory. And finally, I'd like to give a quick summary and outlook. Okay, so let us start from the introduction part. Well, firstly, I'd like to summarize several advantages of the TRG approach, and this is a kind of take-home message. So the TRG approach is a kind of deterministic numerical method based on the idea of the real space renormalization group method. So because of this fact, the TRG is completely free from the sign problem as mentioned by the Fukuma-san in the previous talk. And so let me keep on. So the second point is that this method is a variant of the real space renormalization group method. So typically the computational cost of this method just scales logarithmically with respect to the system size. So it means that we can very easily enlarge the system size by using this TRG approach. And as other benefit, we can directly evaluate the Grassmann integrals by using this method. Here I mean that we do not have to introduce some so-called Schur fermions to evaluate the Grassmann or the fermion system. And also we can directly calculate the path integral itself. So we have a chance to obtain various types of physical quantities from this function. And also I'd like to emphasize that this method is applicable to the higher dimensional systems. And actually the TRG is a kind of, or the typical type of the tensor net, so-called the tensor network method. And the tensor network method is recently very wide. This method is used widely, not only in the particle physics, but also in the condensed matter physics or the quantum information fields. And also its application to the higher dimensional system has a very recently making the remarkable progress. And also the TRG approach can be classified as this algorithm is based on the Lagrangian approach. And also there are other types of approach which is based on the Hamiltonian formalism, and they are sometimes called the tensor network state approach. And this type of approach is also tries to apply to investigate the two-dimensional quantum system recently. But today's my talk, I'd like to focus on the TRG only. So, okay, so let me explain the details. So within this TRG approach, all we have to do is just two things. One is to write down the target function x defined on the lattice as a tensor contraction. And in this talk, I'd like to refer this type of tensor contraction as a tensor network or the tensor network representation of the target function. And the target function is what we want to evaluate numerically. And usually we consider the partition function or its path integral representation as the target functions. And the second task is to carry out the tensor contraction in the tensor network. But actually to carry out this type of tensor contraction exactly is a very difficult task, and usually it is impossible. So we need a kind of approximation technique to evaluate the tensor contraction. And that is provided by the TRG approach. So here is the schematic view of these two procedures. So we have a target function x. We want to evaluate this numerically. And firstly, we re-express this function as a tensor network form like this. And here in the right-hand side, typically the numbers of tensors appearing in this tensor network corresponds to the numbers of the lattice sites. So if we want to evaluate this function in the thermodynamic limit or the zero temperature limit, we need to consider the tensor contraction among the infinitely numbers of tensors. So it is a very difficult task and demanding task. So we use the TRG. And the TRG provides us a kind of Bloch spin transformation for these local tensors, and using this technique to reduce the numbers of tensors in the tensor network form. Okay, so then I'd like to explain the first part by using some simple example, which is the partition function of the two-dimensional classical Ising model defined on the square lattice under the periodic boundary condition. So as you know, this is a typical partition function of the two-dimensional Ising model, and the sigma denotes the Ising spins. And actually, there's various ways to derive the tensor network representation for target functions. But here, I'd like to just explain one way, which is to decompose the nearest neighbor interactions. This is very easy to understand, I think. So let me focus on this one. So we have a local Boltzmann weight or the transfer matrix element like this. And this matrix can be decomposed by using the eigenvalue decompositions or the singular value decompositions. In this case, we can use the eigenvalue decomposition, and this matrix element is factorized into this way. And I have defined the matrix element W in this way. And the point is that in the left-hand side, the original Ising spins defined on the different lattice sites is encoded in the single matrix element, but in the right-hand side, these spin variables defined on the different lattice sites are encoded into the different matrix element. So thanks to this decomposition, we can carry out the integration over the original degrees of freedom at each lattice site independently in advance. And because we are considering the two-dimensional square lattice, by correcting the four numbers of this W matrix element, then we can regard this the result of this integration as a four-rank tensors. And so that by this procedure, we can now have a tensor network representation of the partition function like this. So here is a schematic picture. Firstly, the model is defined on the real space, and we are considering the two-dimensional square lattice, so like this. But by using this decomposition technique and integrating out the original degrees of freedom, we have the four-rank tensor at each lattice sites. And these tensors are in this figure represented by these green symbols. And also in the right-hand side, the internal line is representing the tensor contractions. So that this line means that the tensor contraction between this tensor and this tensor by over this tensor leg. And so that we can have the tensor network representation for various types of lattice field series in this way. But so that our next task is to carry out the tensor contraction. But as I said previously, we cannot perform the tensor contractions exactly because there are too many degrees of freedoms. So the TRG employed the idea of the real space renormalization group. I think we can summarize the idea of the real space or the essence of the real space renormalization group in this way, which is that by repeating a very simple transformation with introducing some proper approximation, then we can investigate the thermodynamic properties as a result of many times of iteration of this simple transformation. But in the traditional real space renormalization group technique, it is very difficult to construct this proper approximation, and it is usually depending on the model you are considering or the geometry or the lattice geometry. But in the TRG algorithms, so to tackle on this, how to construct the proper approximation is very difficult task, but in the TRG algorithms or generally in the tensor network method, we apply the information compression based on the singular value decomposition. Well, here is the singular value decomposition, and suppose we have a M by N matrix A, and by the singular value decomposition, this any M by N matrix is decomposed into the two kinds of unitary matrices, U and V, and we have also we have a singular value, which is denoted sigma k in this slide. And then the singular values always takes non-negative and real values, so we can assume this type of ordering among the singular values. And by truncating this singular values up to truncating this singular values up to, say, D, then we can construct the best approximation of the tensor norm of the original, we can make the best approximation of the matrix norm of the original matrix A. And this is also called as a low-rank approximation of the original matrix A. So the TRG employs this type of SVD technique to reduce the degrees of freedom and perform this type of tensor contraction approximately. And actually, there are several types of TRG algorithms. So let me explain just two typical algorithms, and which can be applicable to the higher dimensional system. One of the traditional TRG approach is so-called the higher order TRG. And this algorithm was proposed by the Chinese group in this paper. And as I said, this algorithm can be applied to any dimensional lattice. And to see the details of the algorithm, let us consider the two-dimensional case. We have a two-dimensional tensor network. And the higher order TRG considers the kind of tensorial SVD for these nearest neighbor tensors. And by considering this tensorial version of SVD, we introduce so-called isometry. Isometry is, in this community, we use the terminology isometry as a kind of a general, is referred as a rectangular version of unitary matrix. So suppose we have and the isometry, we consider the pair of the unitary matrices, and here I suppose that each leg has a size m. And if we take and we consider the pair of the unitary matrix U and U dagger, and if we take the sufficiently large size in this internal leg, say m to the 2, m powered by 2, then this is nothing but equal to the identity. So in this case, we can just inserting the identity matrix into this tensor network. But by using this tensorial SVD, we can introduce the low-rank approximation by using the isometry insertion, and which corresponds to restrict the size of the internal leg up to the D. And usually this truncation parameter is called the bond dimension in the tensor network algorithm. So I would like to refer this truncation parameter as the bond dimension in this talk. And after inserting this isometry, then we carry out the tensor contractions among these nearest neighbor two tensors under these two isometries. And the point is that after integrating after carrying out this tensor contraction, then we again have the four-leg tensors. So this procedure is a kind of coarse graining. So, and the coarse grained, this tensor network has exactly same geometry with the original one. So it means that this type of transformation can be easily repeated. And by one cycle, the numbers of the tensors in the original tensor network is reduced to half. So in other words, by repeating this coarse graining procedure n times, we can approximately contract the exponentially large numbers of tensors in the original tensor network. And this is the algorithm of the HOTRG. And recently, we have another candidate and powerful candidate to investigate the higher dimensional system with the TRG algorithm, and which is the so-called the anisotropic TRG proposed by these guys. And actually, the detail or the algorithmic detail of this anisotropic TRG is a little bit complicated, but the point is that, or the essence of this algorithm is that so suppose we have a similar as in the previous slide, we have a two-dimensional network, and the anisotropic TRG considers a low-rank approximation for each local tensors in advance, and we construct the block spin transformations not using these original tensors, but using these decomposed tensors, and their tensor, they have in this case, the original tensor has a 4-leg, but for example, this type of decomposition, we have two 3-rank tensors, and by constructing a block spin transformation among these low-rank tensors, then we can reduce the computational cost. I mean, the computational memory and the execution time can be reduced by using this type of tensor decomposition technique. And actually, ATRG is nicely can nicely construct the block spin transformation, not using this original tensor, but using these decomposed tensors. Okay, so these are some of the famous TRG algorithms, and let us see their efficiency. Here I'm showing the benchmark results with the two-dimensional classical Ising model defined on the square lattice. And you know that this model, we can exactly solve this model, so we can check the efficiency of the TRG algorithms. And the left-hand side shows the relative error of the free energy as a function of the temperature. And the different curves shows the result obtained by the various types of the TRG algorithms. And you can see that these types of behavior with the fixed bond dimension calculation. And also the right-hand side, I'm also showing the relative error of the free energy, but here in the x-axis shows not temperature, but the execution time. And this calculation is done at the criticality. And you can see that with the fixed computational time, for example, like this, then the ATRG shows a better performance compared with the higher order TRG. So this is a very powerful point of the ATRG. So with the fixed computational time, the accuracy of the ATRG is higher than the higher order TRG. This is a practically important point. Okay, so then here is a current status of the TRG approach, particularly in the higher dimensional systems. We have several choice of algorithms to investigate 3 or 4 dimensional systems with the TRG. And the traditional one is the higher order TRG, and whose computational cost scales like this. And here the D is the bond dimension, and the small d shows the space-time dimension, and the capital L shows the linear lattice size. And this HOTRG has been applied to several spin models in 3 dimensions, or the relativistic fermion, or the lattice gate theory. And also this algorithm has been tried to use to investigate a 4-dimensional system. But currently we have the anisotropic TRG or the triad RG, which was proposed by Kado-san and Nakayama-san. And these algorithms shows a better performance compared with the HOTRG. Actually, their computational cost is very smaller than compared with the higher order TRG. So recently, these algorithms are widely used. And recently, the ATRG algorithm has been applied to, for example, the 3-dimensional non-abelian pure gauge series. And this algorithm is also applied to the 4-dimensional systems like this. And triad RG is also tries to apply the several 3-dimensional spin models, something like this. Okay, so now I'd like to move on to how to extend the TRG algorithms for the fermionic systems. Okay, in the first part, I have explained how to derive the tensor network representation by using the Ising model as an example. But in that time, I introduced the decomposition of the nearest neighbor interactions. And actually, we can do almost the same thing for the fermionic case. And also, actually, there are several ways to derive the tensor network representation for the fermionic path integrals. But here, I'd like to focus on the similar way. I mean, by decomposing the hopping structure, then we can construct the tensor network representation form for the ferromagnetic path integral. So in the left-hand side, I'm showing a typical form of the hopping structure in the lattice fermion theory. And these psi up, psi bar are given by the Grassmann numbers. And we can consider this type of decomposition by introducing the auxiliary fermions. And here, so the eta or eta bars are again the Grassmann numbers. And we can decompose this type of hopping structure into this form. And as similar in the case of the Ising model, the point is that the degrees of freedoms defined on the different lattice sites are encoded into the different exponential factors. And these exponential factors are of the Grassmann parity even. So it is very easy to carry out the integration over the original degrees of freedom at each lattice site independently. And as a result of that, we can obtain the tensor and the original ferromagnetic path integral is now represented by the integration over the auxiliary fermions with is some weight coming from this identity. And yeah, the idea is something like that. So I don't show the explicit procedure, but by integrating out these original fields, finally we have something like this as a result of the integration over the original ferromagnetic field at each lattice sites. Here the eta shows the auxiliary fermion fields introduced by in the previous slide. So the point is that in the ferromagnetic path integral case, the tensor network representation is constructed from this kinds of object. And I'd like to call this as a Grassmann tensor because this is somewhat is a kind of a tensor, but whose leg is not the integer value, but the Grassmann value. But they are at the same time, they are nothing but the multilinear combination over the Grassmann tensors like this. And then we have a coefficient tensor. This is nothing but a tensor in the usual sense. And thanks to this formalism, we can see a very clear correspondence between the usual tensors and the Grassmann tensors. So as I said, in the usual tensor, the indices are given by the integer, but these Grassmann tensors, in this case, the Grassmann tensors indices are given by the Grassmann numbers, and the contractions over the usual tensor is given by the summation over the integer value, which is corresponding to the sum index in the usual tensor. But in the Grassmann tensor case, we can consider this type of weighted integration as a tensor contraction. So thanks to this clear correspondence, it is very easy to extend any TRG algorithm to evaluate the path integrals, including the fermions. And actually, several TRG algorithms have been applied to the various kinds of the lattice fermion models. And here I would like to show some earlier works. One is this is the ATRG calculation of the cold and dense, the ATRG calculation of the 3+1 dimensional non-Wionner-Lashinian model at finite density. And we implemented the ATRG algorithm with the parallel computation. And thanks to this, we can enlarge the bond dimension also in this 4-dimensional calculation. And as you know, that this NGL model at finite temperature and density, the phase diagram is something like this. And in this work, we have considered the chiral phase transition in the very cold and dense regime. And we have calculated the chiral condensate as a function of the chemical potential in this regime. And as I said in the first slide, by using the TRG algorithms, we can very easily enlarge the system size. Actually, we have enlarged the system size up to this, like this. And we take the m to the 0 limit, and the result is something like this. And you can see that there is the chiral condensate takes the finite value, and after some point, this chiral condensate is vanishing. And there is, we can see a clear gap in this chiral condensate. So the resulting chiral condensate by the ATRG shows the first order transition, which agrees with the some expectations obtained by the analytic method, including the mean field or the functional renormalization group method. And here is another application of the TRG to the non-relativistic lattice fermions. And in these works, we have provided the numerical calculation of the Hubbard model at finite density in the thermodynamic and the zero temperature limit. And I'm showing the number density as a function of the chemical potential. And the left one is the model defined in the 1 + 1 dimension. And the right one is the model defined on the 2 + 1 dimension. And in both cases, we can see a clear Mott plateau around the half-filling point. And particularly in the 1 + 1 dimensional case, the model can be exactly solved by the Betti ansatz. So we can evaluate the efficiency of the TRG calculation comparing with some exact result. And for example, in this case, the metal insulator transition occurs at this point. This is the exact result. And the TRG calculation shows a nice agreement in this exact transition point. So again, we can see that the TRG approach allows us to investigate the systems, fermion system, also with the sign problems. Okay. And here is a little bit different topic, but as I said, any TRG algorithm, any TRG can be extended to evaluate the fermionic path integrals. So, and recently these people proposed a novel way to improve the original TRG. This improvement technique is called the bond weighting method. I don't explain this method in detail, but the point is that by using this method, we can improve the accuracy of the original TRG without increasing their computational cost. So this is a very nice improvement of the original algorithms. But the original algorithm is just was formulated on the spin models. So I have extended this algorithm for the lattice fermions and checked that whether this improvement technique is efficient or inefficient for the lattice fermions case. And the answer is that this bond weighting technique also works well for the lattice fermions. And here is the benchmark result of the two-dimensional massless free Wilson fermion. And this line and I'm showing the relative error of the free energy of this fermionic system. And the x-axis is the bond dimension. And this circle symbol shows the original, the computation by the original TRG algorithms. And this line shows the calculation by using the bond weighting technique. And the point is that the computational cost of both calculation is almost the same. So it means that we can restore for example, d is equal to the 100th result with the original algorithm by using the bond weighting technique and just at the d is equal to the 20. So this is a very nice improvement. And also I have provided a sample code of this bond-weighted Grassmann TRG on this GitHub repository. So if you are interested in these algorithms, please visit this repository and git clone it, please. Okay, so then this is the end of the second part. Okay, so then the third, I'd like to move on to the third topic, which is the first application of the TRG algorithm to the four-dimensional lattice gauge theory. And in the following talk is based on mainly this paper. And in this work, we have applied the TRG TRG algorithms to investigate the four-dimensional Z2 gauge Higgs model by choosing the unitary gauge. And here is the action of the D plus one dimensional Z2 gauge Higgs model, like this. And the sigma denotes the matter fields, but in this model, we consider the matter fields also take their value on the Z2. And eta, in the following, I refer the eta as a spin-spin coupling constant. And because the both link variables and the matter fields takes their values on Z2, we can eliminate the matter fields from this action, choosing the so-called unitary gauge, which is defined by this transformation. And by choosing this gauge, we have this action. And there is no matter fields. And here is the first term corresponds to the pure gauge action, and this one is corresponding to a kind of external magnetic field appearing in the Ising model, something like that. Then before I'm showing the numerical result, let me briefly explain why we have studied this Z2 gauge Higgs model. So first point is that this is the simplest lattice gauge theory, but coupling to the matter field. Actually, so far there was no application of the TRG to the four-dimensional lattice gauge theory, so we have started from the simplest case. And by investigating this model, we'd like to check whether the TRG is efficient or not for the four-dimensional lattice gauge theory. And in this work, we have employed an anisotropic TRG algorithm with the parallel computation. And the second point is that also this is a very simple gauge theory, but the model possesses the critical endpoint. And actually, for example, in case of the QCD at finite temperature and finite density, the determination of to determine the precise location of the critical endpoint is a very important task. So I am interested in whether we can specify the location of the critical endpoint by using the TRG technique. And finally, because this model has a matter field, so we can consider the model at finite density. And in case of the Z2, even though consider the model at the finite density, there is no sign problem. But we can consider the model at finite density so that we can see how the critical endpoint moves as a function of the chemical potential. So I think it is an interesting task. And also I believe that it is very important to also check whether the TRG calculation for the four-dimensional lattice gauge theory with the sign problem is very significant. So this work is also in progress. Okay. Then here is a schematic picture of this Z2 gauge Higgs model in the four dimension. And the x-axis shows the inverse gauge coupling, and the y-axis shows the spin-spin coupling. And in this work, we would like to focus on the first order phase transition between the confinement phase and the Higgs phase by calculating so-called average link, which is defined by this. And we'd like to investigate this quantity along this line. And because we must encounter the first order phase transition, the average link has a gap, but moving along this direction, then the gap appearing in the average link must shrink. So then when the gap appearing in this average link vanishes, we'd like to say that that point is the critical endpoint. Okay. Then our study have started from the three-dimensional case, and this is the result of the TRG calculation of the three-dimensional Z2 gauge Higgs model. And this figure shows the effect of the finite bond, the finite bond effect. I mean that this figure shows the first order transition point. And in this case, the beta inverse gauge coupling is set to like this. Actually, this is very close to the critical endpoint. But this transition point, we are showing that this transition point as a function of the bond dimension. And we see that almost no finite bond effect is observed, at least in the position of the transition point. So the TRG very nicely works to locate the transition point. And here is the result of the average link as a function of the spin-spin coupling and varying the inverse gauge coupling. And we can see that the gap emerging in this average link actually shrinks. And to locate the critical endpoint, here I have fitted the gap as a function of the spin-spin coupling by using this fitting form, and also by fitting this gap as a function of the inverse gauge coupling in this form. Here I have carried out these fits independently, but by this looks some rough fitting, but we can see that the resulting critical endpoint is here. And actually, this result is very close to the latest Monte Carlo results. So I think that the TRG calculation for the three-dimensional lattice gauge theory in three-dimensional model is nicely working. Then now let's move on to the higher dimension. So this is the similar result, but the calculation is done in the 3+1 dimension at the vanishing density. And in this case, again, I'm showing the first order transition point as a function of the bond dimension. And the behavior of the transition point as a function of the bond dimension is very different from the three-dimensional case. And we are encountering a little bit higher finite bond effect compared with the three-dimensional case. But for example, the difference between these points, which are obtained at these set to be equal to 48 and 52. And the difference is about 0.057. So I believe that at least for the location of the first order transition point, the finite bond effect is well suppressed. And here is the result of the average link as a function of the spin-spin coupling. And again, we see that by decreasing the inverse gauge coupling, then the emerging gap in the average link shrinks, and finally they are disappearing. And by employing the similar type of fitting, we have obtained the critical endpoint by the TRG calculation with the bond dimension is equal to 52 is something like this. And here I'm showing similar results obtained by the mean field or the Monte Carlo results in the 1980 for comparison. And actually the resulting critical endpoint obtained by in this work shows the deviation from these results. So here is the same result, but I think this is better. So this is the current status of the phase diagram near the critical endpoint. So as I said, the model includes the matter field, so we can consider this model with the finite chemical potential, and also we have do almost the same thing, and we can determine the critical endpoint at the finite density, finite chemical potential case, and I'm showing these results by the blue symbols and the green symbols. And as I said that we see quite deviation about the location of the critical endpoint between the TRG results and the Monte Carlo results. But at least it seems that the TRG and the Monte Carlo share a very similar first order transition line, because here is the triple point calculated also by the Kreuz in the 1980, and here is a triple point, and here is a critical endpoints obtained by the both methods. So it seems that the similar first order line is captured by the TRG and the Monte Carlo, I think. So I think that currently I think that it is very interesting task to to carry out the Monte Carlo simulation on this model by using the novel technique of the Monte Carlo simulation and try to determine the critical endpoint of this model. Okay, so then I'd like to summarize my talk. So the TRG approach does not suffer from the sign problem, and this method is a typical algorithm in the tensor network. Is a kind of tensor network method, and this TRG approach allows us to investigate the thermodynamic limit even in the higher dimensional system. And as I explained, the TRG algorithms can be easily extended to investigate the fermionic systems. And I think as a next target should be the 3+1 dimensional lattice gauge theory coupled to the fermions. And currently the variational approach based on the tree tensor network. This is another tensor network calculation based on the Hamiltonian formalisms, and this group calculated the 3+1 dimensional lattice QED. But the lattice volume is not so large, so I would like to calculate the same model by using the TRG approach and enlarge the system size. And also I'm working on the developing the TRG algorithm to deal with much more the system with much more large internal degrees of freedom. So that's all. Thank you very much.